For each of the chapters that we cover in the textbook, I try to have a lab experiment that sort of reinforces what we've been learning. In chapters 1 and 8, we're talking about measurement, densities, and conversions, and so we're going to be doing experiment 1 this week that deals with measurement and density. If you look in the lab experiment, there are 5 parts, A, B, C, D, and E. We normally don't do part E, so we'll be leaving that off, but we will be doing parts A, B, C, and D. I'm going to demonstrate this more thoroughly as we go into the lab and I take you through the experiment, but just a quick introduction. In part A, you'll be using the electronic balance simply to measure a few objects just to get the hang of it. And it's relatively simple. All we have to do, if the balance doesn't read 0, we simply hit the OT button and it brings it back to 0, and then you can simply weigh anything you wish. We'll be weighing things in all 4 parts, in parts A, B, C, and D. So our graduated cylinder with some water in it weighs 45.47 grams. So part A is simply measuring a few objects of your choice. Whatever you'd like to measure is fine. I'll be choosing those, of course, for you in the online version. The second part, part B, is measuring the density of water. And of course, to get the density, as we learned in class, we need mass and volume. And so we'll be measuring the mass of a sample of water in a 10 ml graduated cylinder and its volume. In parts C and D, we're going to move up to a larger size graduated cylinder because we're going to be measuring the volumes of some metal objects, and we're going to measure their volumes by simply immersing them in the cylinder and observing how much the water level rises. So in part C, we'll be dealing with various unknown metallic elements, and in part D, we're going to look at measuring the densities of some different types of pennies. That's basically the overview of what we're going to be doing. I'll of course go into much more detail when we get over into the lab, but one thing I would like to do, I want to show you guys, I'm going to switch over to my close-up lens here in a moment, and I want to illustrate for you how you read the volume of liquid in a graduated cylinder, because that is the most critical thing you'll be doing today. Getting masses is easy with an electronic balance, but getting the volumes measured correctly, that is very important. If you make a mistake in that, it can have a large impact on your results. So let's go ahead and I'm going to switch over my gear here and we'll take a close-up look at those graduated cylinders. Since we're going to be using both 10 mil and 100 mil graduated cylinders in the experiment, let's take a look at how we measure with each of those and see what the differences are. So we measure the liquid level from the bottom of the meniscus, which would be just about right there. If we take a look at it, the first thing we can tell is we are somewhere between 9 and 10 milliliters. So clearly, the first digit in our measurement is 9. It's 9 point something. Now if we look at it, this is the 9 and this is 9.1. We can tell that because there are 10 markings between the 9 and 10 milliliter mark. So each of these must be a tenth of a milliliter. So we're above 9.0 but below 9.1. So our second digit has to be a 0. And we can be absolutely sure of that. We know that it's 9. We know that it's 9.0. But do we know what the next digit is? And we can't be sure because there are no more markings there, but we can make a reasonably good estimate. It looks like it's about halfway between, so that would make it about 9.05. Now, we don't know if it's exactly 9.05. We can't be sure. So the rule of thumb is whenever you make your final measurement, that last estimated digit, we assume that it could be 1 digit higher or 1 digit lower. So our volume would be 9.05 plus or minus 1/100 of a milliliter. It could be as high as 9.06. It could be as low as 9.04. So even though that last digit isn't exact, at least it gives us a reasonably good estimate. So the 10 mil graduated cylinder can be read to the nearest 100th
of a milliliter. Now when we move up to the 100 mil graduated cylinder, you'll notice that the numbers are 10 milliliters apart, and that means that each of these markings is now 1 milliliter. Again, we want to read to the bottom of the meniscus, which should be just about right there. So our first digit, clearly we're between 10 and 20. So the first digit, of course, has to be a 1. If we count the lines, we have 11, 12, 13, 14, 15, 16. So here's the 16 milliliter mark, and here is the 17 milliliter mark. So we're somewhere between 16 and 17. So clearly it's 16 point something. Now we can go ahead and estimate that final digit. Well, if this is the 16 and this is the 17, I'd guess that's about a 4. It just seems to be a little shy of halfway, so I would call that 16.4. Again, we can't be completely certain that it's actually a 4, but we can be pretty confident it's within plus or minus 1 digit. So we could say that it's 16.4 plus or minus a tenth of a milliliter, somewhere between 16.3 and 16.5. So both the 10 mil and the 100 mil graduated cylinder are able to record values to 3 significant figures. If you've watched the videos for chapter 1 and 8, we had a nice discussion about significant figures there. So we've got 1, 2, 3, and we had the same thing with our 10 mil cylinder. So each of them can read to 3 significant figures, but the smaller cylinder can go out to a greater decimal place, out to the 100th. The larger cylinder can only go to the 10th. If we went to a 1,000 milliliter graduated cylinder, it would only read to the nearest 1 milliliter. So basically, when you're reading graduated cylinders today, you want to record your value as accurately as you can. Don't just call this 16, because you can do better than that. If you can read it to 16.4, then that's what you want to write down. Part A of the experiment is to get you guys familiar with using the laboratory balances. Now the balance over here on the left is our nice modern electronic balance. All we have to do is simply hit that on button, give it a moment to warm up, and when it reads 0.00 grams, it's ready to go. Now over on the right side we have our old-fashioned beam balance, and those are amazingly accurate. I'll show you that just in a moment. But with the electronic balances, things are pretty simple. The first part of the lab simply asks you to determine the mass of 5 objects. So you can pick any objects you wish. So we'll start out with a tweezers or forceps. You simply give the balance a moment. When it beeps, it reads out the mass. So the mass of this is 15.23 grams, and it's accurate to plus or minus 1/100th of a gram. We have a $50, and that would be 22.74 grams. Again, just wait for that beep, and that tells you the balance has finished its reading. My third object will be one of my Expo markers here. When those are full, they weigh about 15 grams. In fact, that's how I decide if I need a new marker. If it gets down to about 12 grams, it's getting low on ink. Our fourth item will be one of our laboratory beakers. That's a 50 milliliter beaker out of the lab drawer, which weighs 29.70 grams. And then for my last object, I will use just my laboratory keys, and that would be 89.12 grams. These balances can weigh as much as 800 grams, and they can weigh as little as 1/100th of a gram. And they can weigh, we have balances in other laboratories in the building here that can go to 1,000th of a gram or even a 10,000th of a gram. All right, now let's compare our nice new electronic balance with this old triple beam balance. It's called a triple beam balance because it has 3 beams. There are 3 little beams across here. The one in the back is increments of grams. It goes from 0 to 10 grams. The beam in the middle goes from 0 to 100, and the one in the front goes from 0 to 100 centigrams, or just a tenth of a gram. Right now, the little beam is right on the 0 mark. So we're going to put our pin on here, and then we'll adjust those weights and see what we get on the old triple beam. This balance is probably at least 70 years old. It wasn't even used when I was a chemistry student back in the 70s, so it probably dates from the 50s at least. So let's move our 10 gram weight out. That's 10. We'll move our 1 gram weight out to the 4 slot because we know it's 14.82. And now let's move our 100th of a gram slider out to, we'll start with 0.82 just to see how it works. Give it a moment just to stabilize. It looks like it is just going very, very close. It might be just slightly high. Let's move it out to maybe 0.83. We'll add another 100th of a gram here. And it looks like we're dead on. So the old triple beam balance, you can tell it's old, it's rusty and dirty. It probably hasn't been cleaned in decades. Yet it still is within 100th of a gram of our electronic balance. It's pretty amazing. The technology may have improved, but chemists could get very good results even many years ago using these old-fashioned types of equipment. For part B of the experiment, we're going to be measuring the density of water. And of course, anytime you measure density, we need a mass and a volume. We're going to measure the density in a 10 mil graduated cylinder. We'll take a close-up look at this in just a moment. So a 10 mil graduated cylinder is marked off in 1/10 of a milliliter increments. So it's pretty accurate. The first thing we need to do is to figure out the mass of our water, and then we'll look at the volume. So we'll start out by weighing the empty cylinder, and it weighs 38.30 grams. It fluctuates just a little bit with the airflow here, maybe 38.29 grams. So we'll record that mass as the mass of the empty cylinder in our lab book, and then we'll take the cylinder off, and now we're going to add some deionized water to it. So we want to fill the cylinder with between 9 and 10 milliliters of deionized water. So we're going to fill this up somewhere between the 9 and 10 milliliter mark. And then we'll weigh it again. And now it's 47.40 grams. Or, well, 47.41. It's fluctuating a little bit again due to the air, but it'll be within 100th or two. So record this mass, and then by simply subtracting the mass of the empty cylinder from the mass of the cylinder containing the water, we have the mass of the water. Now we simply need to figure out what the volume is. As you can see, the water in the graduated cylinder has a curved surface. That curved surface is called the meniscus. And we always measure the volume of a liquid at the bottom of the meniscus. So you can tell by looking at the cylinder that it's marked off in increments of 1 milliliter. And then in between each of those numbers, there are 10 smaller markings, which are tenths of a milliliter. Now you can also estimate your volume in between those markings. You can't be, we can tell for sure what the milliliter is. We can tell for sure the tenth, but we have to estimate to the hundredth. So if you take a look at this, you can see that the bottom of the meniscus is just above the 9 milliliter mark, and it's just slightly below 9.1. So we can make an estimate here. It looks like it's just a little bit below, so I might go with, say, 9.08 milliliters if I was going to make that reading. It's almost to 9.1, but not quite. All right, let's do a second trial now, but this time I'll let you do all the measuring. I'll let you observe and write down your own measurements. So the balance is zeroed, so we'll go ahead and put a fresh 10 mil graduated cylinder on there. We'll let the weight stabilize there, and I'll give you an opportunity to record what you think the mass is. Yeah, then we'll take the cylinder off, and now we will add between 9 and 10 milliliters of deionized water. There we go. And we'll put that back on the balance again. And that'll give you a chance to record that final mass, and then you can again subtract those two to get the mass of the water. All right, you can see that this time the volume is not exactly the same as our first trial, but that actually doesn't matter. Density is what's known as an intrinsic property, which means it doesn't depend on how much of the material you have. If we have a larger volume, we've got a larger mass, and the density should come out the same no matter what. So let's see if your density measurement this time comes out comparable to the one we got in our first trial. For part C of the experiment, we're going to be determining the density of an unknown metal, and then we will use that density to identify it. In the experiment, there's a table that has the densities of 12 different metals, and your unknown is going to have to be one of those, so I've selected one just for us to test. So to measure the density, we'll need, of course, two things, a mass and a volume. The mass is easy. We can simply weigh it on the electronic balance. The volume is a bit more complicated. Our unknown is a whole bunch of little metal beads of different sizes, so it would be very difficult to directly measure those volumes. So we're going to use a method called displacement. We're simply going to measure a certain volume of water in our graduated cylinder, add the metal to it, and then we will see how much the water level rises, and that will be the volume of our unknown. So first, let's get a baseline. So we need to get a baseline mass here. So our cylinder and water without the metal sample, there's our mass, 155.46 grams. Now we're going to measure the volume, and then we will add our metal and repeat. Now look at the bottom of the meniscus and determine the volume of the water in the cylinder before we add our metal sample. We're going to be testing unknown number 25. Now anytime we're measuring a value for an unknown, it's important that we can reproduce our results. So what I've done is I've taken the unknown and I've divided it into two halves, or approximately two halves. So we're going to measure the mass and volume of half the sample and then calculate the density, and then we'll measure the volume and mass of the entire sample, and ideally the two densities we get should come out fairly similar. The density of a substance is what we call an intrinsic property, which means it doesn't depend on how much material you have. If you have an ounce of metal or a ton of metal, the density will be the same. So let's start out with half of our sample. So we've got the mass already of our volume of our water initially. So let's go ahead and take the metal, and we'll add half the sample. And now we'll measure the new mass. So record this mass in your lab book, and then we can subtract the mass of the cylinder and water without the metal, and that will give us the mass of the metal. Now we simply need to record the new volume, and then we can subtract the original volume from that, and that will give us our volume, and that will be give us the density of half of the metal sample. As you can see, the volume of water in the cylinder has increased due to the addition of the metal. So record the volume by reading the cylinder at the bottom of the meniscus, and then you can subtract the original volume from this new one, and that will give you the volume of this first half of the metal sample, and from that you'll be able to calculate our first density. Let's go ahead and measure the mass and volume of the second half of the metal. So we'll go ahead and take our graduated cylinder and we'll add the remaining metal sample. And that will give us now our mass of the entire sample. So be sure and record that in the table in the lab, and then we'll go ahead and measure the volume, and from that we can get our second density. Now determine the final volume of the water with the entire sample, and then you can use that and the previous volume, determine the volume of the entire sample, the mass of the sample, and then calculate your second density. And then take those two densities and average them together, and then compare that value with the values in the table of the known samples, and you should be able to determine the identity of your unknown metal. For part D of the experiment, we're going to be measuring the densities of pennies. Now, pennies have been made out of different metals over the years. In 1909, when they first made Lincoln cents, they were made almost entirely of copper. So the density of those pre-1983 pennies, the older ones, will be copper. In 1983, they switched to zinc. Copper simply became too expensive, so they started making pennies out of zinc. These are nice new pennies. You can see how shiny they are. There's a thin layer of copper on the surface, but underneath it's simply a piece of silver zinc. So the copper still makes it look like a normal penny, and it keeps it from corroding, but it's going to have a different density because now the density will be similar to that of zinc. In 1943, for 1 year, because there was a shortage of copper during World War II, they made pennies out of scrap iron. So they took old steel, made pennies out of it, and as you'll see in a few minutes, steel pennies have a tendency to rust. So what they did is they plated those pennies with zinc, and that made them nice and bright and shiny silver. But over the decades, that zinc coating is worn off, so the pennies we'll be using today, you'll be able to tell, look a bit rusty. So let's start out with our post-1983 pennies, the ones they made after 1983 that are mainly made of zinc. The first thing we'll need to do is to measure the initial mass and volume of our cylinder with water in it. So I've added about 50 milliliters of water, and then we can record the mass, and then we'll go over to our light box and determine the volume, and that will be our starting point. Again, as we did in the previous experiment with the unknown metal, we're still using the 100 mil graduated cylinder, so don't forget that the increments on this are each 1 milliliter. They're numbered every 10 milliliters, but the individual markings are each equal to 1 milliliter, and of course you can estimate in between those markings to the nearest tenth of a milliliter. Now let's go ahead and add our 50 pennies that we've counted out. These will again be the post-1983 pennies, so we'll take the cylinder off for a moment here. Go ahead and pour our pennies in. And then we'll measure the mass once again. And that will give us the mass of the water and the pennies in the cylinder, and then we can simply subtract to figure out the mass of the pennies. Now you can record the new volume of water with the pennies in, and then using the difference between the two volumes and the difference between the two masses, you can calculate the density of the post-1983 pennies. Next, let's take a look at some 1943 pennies. As I said before, they're made out of steel, and originally they were coated with zinc, so they were very shiny, but as you can tell, they've become rather rusty over time. So again, let's start out by measuring the mass and the volume of water in a graduated cylinder. So I put approximately 50 milliliters of water in there. And the mass in this case is 154.26 grams. All right, so record the volume of water in the second cylinder. This is the one we'll be using for the 1943 steel pennies. Let's go ahead and add our 50 steel pennies to the second graduated cylinder. There we go. Now we can get the mass of the pennies. And here's the final volume of our 1943 pennies. All right, let's wrap up our experiment here with the density of the pre-1983 pennies. These are the ones that are made almost entirely of copper. You can tell they're not quite as shiny as our brand new pennies. So we'll begin, as always, by measuring the mass of our cylinder in water for our baseline. And that looks to be about 152.81 grams. Now record the volume of water in the third cylinder for the pre-1983 pennies. Now let's go ahead and add the pennies to our graduated cylinder. And we'll get the mass of the pre-1983 pennies. And now record the volume of water with the pre-1983 pennies. And then we can use that information to calculate the density of those pennies.